This is our second video in our discussion of operating systems. In the previous video, we covered several slides talking about operating system functions and layers of the operating system and device drivers. In that video, we discussed functions of the kernel and the service layer. What we're going to do in the next set of slides we're going to cover is dig a little deeper into the kernel issue of hardware allocation and resource allocation, both hardware and other types of resources, and a little more into the service layer and its size. But we're going to spend most of our time talking about resource allocation. Okay, so skipping forward a few slides, here's the one we're going to cover on service layer. So as we discussed in the last set of slides, the service layer contains a large set of utility programs or functions or subroutines or methods, whatever you want to call them. And each of those does one fairly well-defined task on behalf of either an application program or on behalf of the command layer or one part of the command layer of the operating system itself. And examples of these kind of functions include things like controlling windows on a graphical display, handling packets incoming and outgoing to and from the network, taking care of input and output going to a disk, opening files, closing files, reading them, writing them, so on and so forth. Okay. So over time, of course, computer hardware has vastly increased in capability. Software has had to be created for that. Well, they're not new anymore. New forms of hardware and capabilities such as graphical user interfaces. I mean, these basically didn't exist prior to the mid to late 70s. And what has happened is that as the hardware has become more complex, as new types of hardware have been added, and as software capabilities have been added to take advantage of that more complex or newer types of hardware, the number of these service layer functions has just exploded. Whereas an operating system in, say, the late 50s or earlier 60s might have had a few dozen, maybe 100 utility functions or service layer functions. An operating system today probably has tens of thousands, and it basically boils down to the complexity of the types of things we expect the operating system to do on behalf of the application programs or of the service layer. A quick example of this: the service layer, and this isn't an exact match, but it's close enough for this discussion. In a modern Windows operating system, the set of services offered by the operating system to application programs and the command layer is contained in something called the .NET Framework Class Library. Okay. And these classes and their associated methods are essentially those utility functions or service layer routines. Now, it was interesting because before I started recording this video, I thought, man, there must be a master list of these somewhere, and I went digging for it. And there isn't a master list in the sense of there's one document that lists every single function call or subroutine call or method call. And one of the reasons is there's just too many to put into one document. So as you note on the table of contents here to the left and on these namespaces to the right, because there's so many, they basically had to categorize them. And so as we kind of just peruse down this list, we see, okay, well, here's one for running JavaScript. Here's one for interacting with a SQL server, a database server. Here's some specific to development languages such as Visual Basic or Visual C. Here's a Win32. This is actually an interface to older Windows functions. Here's one for Windows themes. What else do we got? We got a lot here under the heading of system: diagnostics, data, configuration, directory services, input-output or I/O, systems management functions. What else we got here? Well, we got one in particular I want to dig into. Here's the one for Windows. So basically anything that would constitute an aspect of a graphical user interface, from a full-blown window to a menu to a button to a pull-down list, would be covered, would be within this group called system.windows. So if I click on it, let's see. you can see that has a further set of categories. So I've got things like automation, I've got things like controls. So controls would be things like, buttons and other things I can click on. Data, documents, forms. I've got subcategories of forms, layout, design, what have you. Visual styles, input. What else we got here? Let's see, media, so, multimedia files, sound and video, shapes, threading. And we'll talk later in the chapter about multi-threading operating systems and controls of multiple threads. But as you can see, there's just a huge number of categories. I mean, and if I clicked on this, then we would go in and we would look at the class and we would see probably there's under controls, there's probably, God knows, probably maybe 50 or 100 different functions. Okay, so you get the idea. The service layer of a modern operating system is huge. And the reason it's huge is because there's so much we expect it to be able to do. Okay, and because because that has to cover a wide range of input, output, network, the various hardware devices, control of programs and processes and threads, authentication, access controls, you name it. It's all under the banner of the operating system, and it all winds up being a function or method or a set of methods inside the operating system. So, why is this such an important issue? Well, it boils down to a very simple phrase which has some pretty significant economic implications, and that phrase is code reuse, where code are the actual program instructions contained in each of those utility functions. Okay. So as we've said before, an application program does things like input-output, okay, by calling a subroutine or a method that's sitting inside that operating system service layer. Okay. Each time that application program calls one of these methods, it is in essence reusing code that's embedded in the operating system that some programmer already wrote. Okay. So think Windows again. Windows got big old corporate headquarters up there in Seattle. Thousands of programmers working for Windows, many of them concerned with writing or updating the service layer for the next version of Windows, whatever that might be. Okay, so in essence, every application program that runs under Windows is reusing the work of those thousands of programmers up there in Seattle. And every time you run one of those programs and say it opens a window, or you click the minimize button, you are in essence reusing code somebody wrote. Actually, probably somebody wrote it back in the 80s or 90s, and it's been updated God knows how many times since then. Okay. What are the advantages of code reuse? Well, they're basically two obvious ones, and then a bunch of ones that follow from that. The first is application programs are simpler. So if I want to write a typical Windows application, I don't need to know, quote unquote, how to minimize a window at the level of, okay, how do I clear the screen and redraw the background once it's there, and how do I make sure that it shows up on the taskbar after I've minimized it, and how do I make sure that when the user clicks it on the taskbar, it pops back up and displays as it should. How do I ensure that when my window is displayed, if another window gets displayed over top of it, that I'm not overwriting that window that's displayed on top of it. I don't have to write any of that code. As an application programmer, that stuff I don't have to write. I just have to call or execute the service layer functions that are already there. Okay, so application programs, I mean, if you look at a typical application program as it would exist before you, quote unquote, add in the code from the service layer and after, it's not unusual to find that the quote unquote application programmer wrote really 5% of the code and 95% of it is in the service layer and reused. Okay, so what are the advantages of that? Well, one obvious one, cheap. Okay. Now, yes, the application programmer has to know which service layer functions to call, to do whatever, has to know what data to pass them, has to know what results expected to be passed back, has to know what error codes might arise, and so on and so forth. But that's much simpler set of knowledge and much less complicated task than having to actually write that code. Okay, so from the application programmer standpoint, it's a lot cheaper to develop initially and to update later. Okay. In addition, the types of things that are embedded in the service layer, some of them are pretty complicated stuff. So, for example, dealing with communication amongst multiple threads in a process. Okay, that's something that vexes people with master's degrees in computer science. Okay. And they don't always get it right. So if we forced anybody who wrote a multi-threaded application to be able to know all of those algorithms and to be able to reliably write code on them every time, basically all of our programmers would need roughly the equivalent of a master's in computer science. Okay. That's a pretty high bar. And of course, if you look out in the world of software development today, well, yeah, there's plenty of people with masters in computer science walking around, but there's people with bachelors in information systems and bachelors in computer science. There's people with a technical degree or associate degree, and there's a whole bunch of people who just taught themselves on the weekend or the evenings, with the, learn whatever language it is in 21 days book in their lap. Okay. Many of those application programmers who don't have years and years of formal training are perfectly good programmers and they write very useful code. But they can do so because they need fewer skills to write programs than if there was no service layer and they had to have skills that covered the entire gamut of those service layer functions. If they needed to know about disk drives and graphics and multi-threading and inter-process communication and network I/O and the list goes on, would take a long time to acquire those skills. Okay. So this issue of code reuse is one basically of economics. Okay. Because because the service layer is there, application programs can be simpler. They're faster to write, they're cheaper to write, and the people who write them don't need as much training. Okay. So it's really an issue of economics. Okay. The last issue, which we've already sort of touched on, is that by providing this service layer and having all application programs use it, it becomes much easier to put important resources under exclusive control of the operating system. To the extent that all access to those resources goes through a service layer routine, it becomes much easier for the operating system to, enforce allocation rules that prevent programs from interfering with one another. It becomes much easier to enforce security, okay, amongst a host of other things. Okay, so this service layer, it's something that didn't exist in the early days of computers. It's something that's incredibly big and ugly in the modern world of computers. And despite its ugliness and the fact that, people, especially computer types, often complain about it, the fact is this approach is here to stay, and it's here to stay because code reuse makes economic sense. It also makes operating system sense. Okay, so I don't see any downsizing trend in service layers in the near future. Maybe we'll bust them up into pieces that can be independently installed and updated, but I don't see the size issue going away anytime soon. So enough on the service layer. Let's move forward with our more in-depth discussion of resource allocation. And for this discussion, I want to back away from computers for a minute and just talk about the concept of resource allocation in general, because it's a problem that pervades many fields besides computing and operating system. Okay. So what's the basic issue here? Well, the basic issue is that whenever you have multiple things, those things could be programs or threads. Those things could be people. Those things could be governments. Those things could be businesses. They could be educational institutions. They could be departments within educational students or educational institutions. They could be students pursuing a degree, so on and so forth. Whenever you have multiple things competing for access to a limited set of resources, so for example, we've got some examples here. So whenever you have multiple departments or employees competing for budgetary dollars, whenever you've got packages competing for space in trucks or planes or warehouses, whenever you've got vehicles competing for access to crowded roadways and intersections, whenever you have students competing for access to classes or seats in classes, you have a resource allocation problem. Okay, so what is the nature of that problem? What are the decisions involved in it? Okay, well, there's a bunch of them, but this is a pretty simple and relatively comprehensive set. First off, who or which thing gets to use which resource? Okay, which resources are you allowed to use? Okay, which resources of those that you're allowed to use can you use right now? How long can you use them? How much of that resource do you get? Do you get it now or do you get it later? When you do get it, do you get it forever or do you have to give it up at some point? Okay. These are basic questions of any sort of resource allocation task. So if I allocate budget to a department, okay, how much money do they get? Do they get it now or do they have to wait 6 months? Okay. Do they get to use it for 6 months and if they don't spend it, they have to give it back? Okay. So basic questions of resource allocation. Now, one thing, good or bad, depending on your point of view about resource allocation, is the complexity of the job. Think of resource allocation as a job being performed by a person. Okay. As the number and diversity of the resources and the competitors for those resources rises, okay, the complexity of the job associated with resource allocation goes up. It becomes a harder job. Maybe it becomes too big a job for one person to do. So for example, let's say we're handling budgeting or room scheduling. Okay, take your pick. Okay, and I'll give you two ends of the continuum here. End number one, 4-room elementary school. So we're out somewhere in the hinterland and, in deepest, darkest rural New Mexico, and there's a 4-room elementary school. Okay, say we got grades 1, 2 combined, and grades 3, 4 combined, and grades 5, 6 combined, and we got a kindergarten. Okay, so there's your 4 rooms. Okay, 4 rooms, 4 teachers, and there's probably a small office for a secretary or something like that. Well, maybe there's a conference room. Well, how tough is room scheduling in that environment? Well, probably not very tough, okay? I got 4 teachers, each of them gets 1 room, and they pretty much keep it for the whole year. I got a conference room, and, sometimes people need it, sometimes don't. Maybe I got a piece of paper stuck on the front of the door, and, if you want to reserve the room, you walk by and you just write your name on there and the time you want it and the day you want it, okay? Not a very complicated thing. Even if we start talking about budgeting, probably not that complicated. I mean, what do we got? We got 4 teachers and a secretary. Okay, we got to maintain 1 building. We got to buy supplies for 1 building. Okay, it's probably something a bookkeeper can handle, in less than 10 hours a week. Okay, now let's take the other end of the spectrum. Let's talk UNM. Let's talk 25 to 30,000 students. Let's talk 1,200 full-time faculty, God knows how many staff, an attached hospital, a fleet of vehicles, so on and so forth. Okay, how do you handle room scheduling for UNM? Well, trust me, it's not simple. Just deciding, say, 4 months before the semester starts, which classes are going to be offered in which rooms is a very complicated task. Okay, obviously, the size of the class or its maximum enrollment has to be matched to the type of room, but sometimes technical capabilities have to be matched too. Is this a room that, is going to be for an organizational behavior class where we're going to do a lot of group breakouts and we want some movable furniture? Or is this a more traditional lecture hall room where we can just go with a big projector up front and a stage and have a bunch of seats up in a tier with people sitting there basically passively taking in the lecture? Or is this, say, a class that's going to be taught in a computer lab where I need computers and projectors and so on and so forth? So matching the capabilities of the room or the resources in the room to the resources required by the various classes is not an easy task. And of course we got things other than classrooms. We got conference rooms, we've got offices, we've got so on and so forth. How about the budget? Well, maybe the budget of the 4-room elementary school is, I don't know, let's just pick a number, say $200,000 a year. UNM's budget's more on, along the lines of $200 million a year. Clearly that isn't something that a bookkeeper is going to handle 10 hours a week. Okay, so the point here is that as the number and diversity of both the people or things competing for the resources and the resources themselves goes up, the complexity of the job of resource allocation goes up. All right, so now let's come back into the computer world. Back to the earliest days of computers, okay, where there basically was no operating system. Or maybe there was an operating system, but it was very primitive. Okay, but maybe there was an operating system, but it only allowed one application program to run or execute at a time. Okay, that's an example of what's called a single tasking operating system, where each task is in essence one application program. As we'll discuss later in the chapter, there are other ways to measure tasks, processes, threads being two examples. But for now, we'll just assume program is the basic unit. So a single tasking operating system supports one program at a time. Okay? In the world of single tasking, resource allocation is pretty simple. Why? Because there's no competition for the hardware resources. Okay? There's basically two ways you can do this. One is operating system. Who needs an operating system? You just let the application program do all the resource allocation itself. Since there's only one application running at a time, there's no competition for the resource. Maybe there's competition for the time slot, but once the program starts running, it owns the hardware in its entirety. It can do whatever it wants, doesn't have to ask anybody's permission, doesn't have to worry about stepping on anyone else's toes. Another way to do this, and this would be late 50s, early 60s, we have a fairly simple operating system, okay, to manage resources used by programs over time. So for example, files on disk exist over the course of many programs running. Files on disks are relatively permanent, whereas running programs come and go relatively quickly. So we may need to do some fairly simple resource management with respect to the files on disk, okay, and with respect to things like starting and stopping programs. But once again, since we're single tasking, while a program is running, it's really only competing with itself and this simple operating system for resources. Okay. So in either case, the set of decisions to be made regarding resource allocation is relatively simple. Okay, because the only programs in competition are the operating system itself and whatever application program is currently running. So now let's up the ante. Well, single tasking may have been fine in the 50s and early 60s, but in the modern world, and for quite a few decades preceding this, something called multitasking has been the norm. Okay, multitasking is when multiple application programs can run at the same time. What do I mean by multiple application programs running at the same time? Well, let me just fire up a few windows here that I actually have open on this system, but you can't see because I'm running on my right screen and not my left screen. Well, there's my email, and let's see, there's my web browser, and there's an Excel. There's a piece of an Excel spreadsheet, and let's see what else we got running on here. Okay, here's a piece of a Word document. Here's an open web editing session I have, so on and so forth. Oh, and by the way, I've also got the recording program running that's creating this video. So right now, I'm just going to count across my taskbar. I've got Internet Explorer, Outlook, Excel, Word, Expression, Adobe Acrobat, and the Camtasia recording software, all running at the same time. Okay. Now, the reality is probably in terms of me interacting with the program, only one of them is really, what shall we say, on top at any moment. But they're all running. They're all active processes being managed by the operating system. They all have resources allocated to them, memory, what have you. As I click on them in the taskbar, they grab CPU resources. Maybe even while they're just down in the taskbar, they're grabbing CPU resources because they're doing things in the background. Okay. So early operating systems didn't do multitasking. Why? Because they couldn't. Okay. The hardware resources were simply too limited to support multiple application programs. Okay, how many programs can you fit into 4 kilobytes of RAM? Not a whole lot. You talk about 4 gigabytes of RAM, now you can fit a whole bunch of programs in it. Okay, so as the hardware capabilities went up, in particular RAM and CPU, multitasking became possible and eventually even desirable. And so really along around, I'd say, in the mainframe world by the early 80s, in the PC world or microcomputer world by the mid-90s, multitasking was pretty much the dominant form of operating system. Okay. So we know what's good about multitasking. Allows us to do multiple things at the same time, makes better use of all this, tons of CPU and RAM resources we have. But what's the cost? What's the catch? Well, the catch is that multitasking has just increased competition for resource allocation by the operating system. It ups the ante, makes it much more complex. Okay, some examples. Now when the operating system makes resource allocation decisions, it has to be concerned about whether programs are interfering or hurting one another. Okay. With respect to all the various resources, be they open files, be they, pixels on the screen, be they CPU cycles or memory blocks, we need fairly elaborate accounting methods to keep track of which resources are currently unallocated, which ones are allocated, and to which programs they are allocated. So think of a whole bunch of accounting records that change fairly quickly, keeping track of all this stuff. Okay. Decisions about allocating those resources have to be made very quickly, and they're changed very quickly. Programs start, programs finish. Programs go idle, programs are brought to the top. Okay. The application environment changes rapidly, and as a result, the accounting updates to these accounting records that keep track of free and allocated resources, they have to happen very quickly too. And by the way, we want to do all these things, these first four, in a way that doesn't impact performance, okay, or in a way that optimizes performance. And that's really a two-edged sword, only one of those edges of which is shown here. So for example, if I've got multiple programs and they all want to run right now, say they're all background programs and they're all screaming to the operating system, give me the CPU, give me the CPU, the operating system has to kind of take a holistic view and say, well, which one should get, what's the best use of this CPU at the moment? Do I want to allocate it to the interrupt handler that's about to move some data from the disk drive into memory? Do I want to hand it off to the subroutine that's, reading incoming network packets, or do I want to do something else with it? Okay, and that's not always a straightforward decision. Okay. Resource allocation is management. Well, is a key function of management. Let's put it that way. Okay. So if you look inside any modern organization in the world, be it company, government, educational, whatever, you've got people, managers inside that organization, and one of their most important jobs is to either make the allocation decisions themselves or to set the policies that constrain those allocation decisions. So either a manager is making the decisions or they're setting the policies, and those policies in turn are implemented by other managers or by some sort of automated program. Okay. Managers are also responsible for accounting for the resources. Okay. Although once again, that's a task that's usually delegated. We hire accountants to keep the books for us. We hire people to do scheduling for us. We may set policies by which those things occur, but we don't necessarily as managers do them ourselves. Okay. So if I'm designing an organization, okay, set of job specifications if you like, I know that these types of resource allocation decisions have to be made, and I know they're very important. I know I'm going to need some people to help make them or set policies that help make them. But there's a real key question in that organizational design, which is how many managers do I need and how do I distribute the work amongst them? Okay. Why is this such an important decision? Well, it's an important decision for two reasons. One is, first off, the number and the work distribution will affect their efficiency. Okay. If I hire too many, maybe there's a bunch of them sitting around twiddling their thumbs. If I'm hiring too few, maybe they can't do a very good job. If I hire the right number, but I divide the tasks up amongst them in some insane way, maybe they're spending all their time, reading emails and trying to coordinate with one another and not enough time doing the actual decision making. Okay. So there's both a question of number and of the distribution of work amongst them. But a key issue here that you need to realize, and this is that second point that I skipped over at the end of the previous slide, is a concept called system overhead. And the system overhead concept is very straightforward. System overhead is a way of looking at an organization that says, okay, There are people who quote unquote do the real work. If I'm in a factory, there are people who, move the parts from the warehouse to the production line. There are people who assemble the parts or machine the parts or test the parts or whatever it is that, is going on in that factory. They're quote unquote doing the real work because the real job of the factory is to make things, okay, that we're going to sell. Anybody in there doing management, okay, a supervisor, whether they're doing resource allocation or something else, they're system overhead. Okay. Any money we spend on them is money that is at least not in a direct sense doing quote unquote the real work. Now, if we're spending money on quote unquote good management that helps the people who do the real work be more efficient or produce better quality or what have you, then there is in fact an economic benefit, okay? But maybe the system overhead is too high. Maybe I've got too many managers and they're interfering with one another, okay? The proverbial, city work crew, road work crew where you got one person digging the hole and 4 supervisors around, watching the guy work, okay? So you're always going to have system overhead. The question is it good system overhead? Is it too much system overhead? So let's look at some of the key goals that an organization or a manager will look at when they're doing the resource allocation. Well, number one is we want to minimize the resources consumed by the management functions. And that leaves more resources available to quote unquote do the real work. We want the smallest management possible that enables more efficient work. Okay. And it's not as if there's some magic cutoff above which, there's no improvement. But kind of think of it as your classic economic curve with, supply and demand. There's a right amount of management that matches up to a right amount of work. Okay, and that's the spot we want to be in. We want to be where those two lines crossed. Okay, we want to have just enough management to ensure that the components doing the real work are able to do that work without interfering with one another and do it efficiently. And any decisions that we do make, we want to make them in such a way that we're maximizing the productivity of the organization as a whole. So if I've got a warehouse manager and a line supervisor out on the production line, I want each of them thinking about the overall productivity of the factory when they make their decisions. Because if they're making decisions in isolation, well, the guy in the warehouse might say, well, I want somebody to sign 3 different forms, before they can pull out a part to carry to the inventory because I'm making sure my inventory is, under good control. Well, that may be fine, but that may make for a very inefficient movement of parts from the warehouse onto the production line. Okay. So decisions, even if they're distributed across multiple managers or multiple management entities, as they often are, need to be made in a sense of global or organization-wide maximization or productivity. Not always an easy thing to do. Okay, let's put a little flesh behind some of these concepts. Okay, we've got a very simple exercise here. And it asks you to consider 2 kinds of kitchens. Okay, kitchen number 1. Imagine you and a friend have, got tired of the corporate rat race and you've decided, hey, catering's where you want to be. Make my own hours. I love to cook, interact with people. People who are eating are usually happy, assuming they're not eating, totally crappy food. So you and your buddy, you set up a catering company, you run it out of one of your kitchens, whichever one you've got the biggest one. You go out and lease a little truck, a little delivery van. Okay. And, that's your job. So how often is that company going to get orders? Well, how many orders can 2 people fill in, say, a week? Okay, well, probably not more than a dozen or 2 at most. Maybe you do a couple of breakfasts here and a couple of lunches there and a couple of dinners there. And on a really busy day, you got a breakfast and a lunch and a dinner, although it's kind of hard to imagine being able to cook, deliver, and serve all that. But I guess if you put in a 14-hour day, you might be able to pull it off. Okay, so orders arriving, a couple dozen a week, maybe max. What resources do you need to fill those orders? Well, what do you got? Well, obviously you got the basic foodstuffs that you're either going to prepare or cook or combine somehow to create the things that you're going to serve. Okay, you've got the labor, you and your buddy, that goes into making those. Maybe you bring in an hourly employee every now and then, or get one of your cousins to come in and help when you're a little busy. You've got the actual foodstuffs in the fridge or the pantry or whatever. You've got probably a bunch of kitchen utensils. You got pots, pans, what have you, serving dishes and the like. You probably have a few portable, like a portable cooler or a portable heater to shove on and off the truck. You got the truck itself, the gasoline that goes in it. That's about the range of it. Okay. More to the point here, how do you coordinate the use of those resources? Well, with only two of you around, the job of coordination becomes, relatively simple. I'm not saying it's easy, but compared to a much larger kitchen, it is relatively simple. Okay, so, say you've got you're preparing a lunch order to feed 30, What do? Well, the two of you, I'm sure you probably divide the labor somehow. You work on the entree and, your friend works on the desserts, and when it comes delivery time, maybe you take care of one half the order and he takes care of the other, and you do a similar sort of division of labor when you're actually serving. And if you need some coordination, well, the two of you are right there in the same room. You just talk to one another. Say, hey, I'm running a little behind on the entree here. Can you give me 20 minutes to work on this? Or that person says, hey, I'm running a little behind here on this. I need to decorate this cake. Can you make the iced tea or something while we're at it and put it in the dispenser? So coordination just isn't that big a deal because there's really only two people. Okay. Likewise, hopefully it's a big enough kitchen, but probably not too big a kitchen, big enough for you not to run into each other every 30 seconds. But, chances are there are some things you have to coordinate. You both can't use the oven at the same time unless what you're putting in there is exactly the same temperature, and unless there's enough room in there for both things. So there's probably a few resources that are limited that you actually have to quote unquote schedule. And let's talk about scheduling. You've probably just got a simple schedule tacked up on the wall. Well, tomorrow we got a lunch and a dinner, but we don't have a breakfast. So we're going to come in about 9 in the morning to start working on the lunch. We're going to finish it by 11. We're going to drive there, get there about 11:30, set up, and it'll be ready to go at noon. Leave at 1:30, come back, clean up. That'll be just enough time to prep the dinner. And maybe there's something at the dinner that requires a real long lead time, so we'll come in at 9 instead of 10 and we'll pre-start. We'll do a little bit of work ahead from 9 to 10 on the dinner before we start working on the lunch. Okay. But once again, this coordination process isn't that big a deal. And so the system overhead associated with it, the amount of communication associated with it, and the formality of it's just not going to be all that high. Now let's go to the under end of the scale. A large kitchen in a busy restaurant, hundreds of customers, dozens of employees. And I went out on YouTube and actually found a picture of this. So I'm just going to let this thing run for a couple minutes. So those of you who have never had the joy of working in a commercial kitchen can get a rough idea of just exactly what we're talking about. This is La Bastide Saint-Antoine restaurant in Paris.
T'as les étiquettes là, les petits couverts, souvent, ils sont là, les couverts. Effectivement, les boules, tu cherches. Ah, puis on va sortir. Les gars, c'était demain. C'est bon. Il n'y a pas de... pas trop tout bon. Tout bon. Ça dit que c'est avec les affaires.
Okay, so now you've seen 2 minutes in a busy commercial kitchen. Okay, I don't know if that was in the hundreds of customers range. It was probably in the at least 100 customers range. I would say maybe even a little bigger. Dozens of employees, ignoring the ones in the black vests and bow ties, who would, I assume, are waiters and waitresses. I counted roughly 12.5 people running around back there. So, how often do orders arrive? Well, typically in a restaurant, of course in Europe people tend to take a little longer to eat, but let's just take some round numbers. Let's say I got 100 tables, average of 3 people at a table, that's 300 people. Table turnover, say, let's say every hour. So that's 300 orders per hour. Okay, and of course sometimes you get multiple orders per person. They'll order the entree and then they'll order dessert, or they'll order an appetizer and then they'll order an entree and then they'll order dessert, and so on and so forth. So you're looking at several hundred orders coming in and out of there in the space of an hour. What resources are used to fill the orders? Well, back in the 2-person kitchen we had 2 people. Okay, now we've got 24 people. We've got lots of ovens, we've got lots of counter space, we've got lots of burners, we've got lots of pots, we've got lots of pans, so on and so forth. Okay, so clearly the number of resources, both labor and otherwise, is substantially larger. How do the employees coordinate their use of resources? Well, that's a good question. Different kitchens will handle this differently. But if you were to back up and look at that video, actually, let's do that very quickly here. I'm pretty sure this guy right here is the head chef, although he's not wearing one of those big tall caps. Maybe that's only something they do in America. Okay. I'm pretty sure of these other people milling about, there's probably 2 or 3 of them who would be quote-unquote his lieutenants. And I would imagine there's some division of labor amongst those lieutenants. So some of them are concerned with entrees, and some of them are concerned with side dishes, and some of them are concerned with desserts, and so on and so forth. And then you saw a bunch of other people running around who, didn't seem to be responding to commands from others. So there's probably a hierarchical organization where this person is in charge. There's 2 or 3 or 4 others underneath of him that are kind of, next level managers. And then there's a dozen or so people who are quote unquote doing the real work. Although it looks like these managers are doing plenty of the work as well. Okay. So how do these employees coordinate their use of resources? Well, if these second-level cooks or second-level chefs are specialized by the type of thing they're working on, then that's one form of coordination. We've divvied up a big task into a bunch of smaller tasks, and one purpose in doing that is to minimize the amount they have to talk to one another. Okay, so I know what I need to do to make bread, and you know what you need to do to make desserts, and you know what you need to do to make meat entrees and things like that. So we don't have to talk to each other about maybe things like ingredients or what have you. But certainly we do have to talk to each other about shared resources, like, for example, all this counter space in here, or these burners in the middle, or the ovens that were in the other room, or so on and so forth. And there probably has to be some significant coordination in terms of, who gets to use the oven when and for how long, and, you got to be out in order to make room for this guy to come in and do his thing. We can't occupy all the ovens or all the burners for cooking the entrees if we haven't yet baked the bread, or if there's some prep work that needs to be done on desserts that requires any of those things. Okay, so the amount of coordination is pretty high. Okay. So my point in here, it was simply to illustrate with a fair amount of specificity the difference between large and small and the implications of that for the complexity of resource allocation. Backing up to the earlier slide, where did we cover that? Okay. So this is clearly the commercial kitchen was a multitasking environment. There were an awful lot of things going on at a time. Okay. Decisions had to be made in such a way that the programs don't hurt one another. Okay. I, as one cook, don't want to do something that, ruins something another cook is doing. I'm not sure how much accounting was going on in there, but certainly somebody, is keeping track, at least in their head, of, who's using what space and who has access to what ovens and, which of the, which of the assistants are working for which people and so on and so forth. Okay. Clearly, this is a dynamic and quickly changing environment. Okay, the decisions have to be made dynamically in real time, basically in response to the orders that are showing up. Okay, and that application environment changes very rapidly, so the decision making has to be very rapid. And by the way, most of these decision makers are also actually doing real work. They're cooking. So the less time they spend making decisions, the more time they actually have to be cooking the stuff that's going to be sold to the customers. Okay, so the implication of this for computers is pretty straightforward. A multitasking computer has a much tougher job, much more complicated job associated with resource allocation. The operating system of a multitasking computer is much more complicated, therefore, than the operating system of a single tasking computer. And in the world of multitasking computers, a multitasking computer with thousands or tens of thousands or hundreds of thousands of tasks to allocate resources to, say a mainframe, obviously has to have a much more complicated operating system than, say, the operating system that runs on your PC. That'll do it for this video.